Right, so I'm gonna go over the practice exam. Right, so I already posted the solution, but I will go over it again. So chapter 17. Right, so it's about equilibrium constant and the equilibrium positions and how to determine the direction of a reaction. Right, so for the first problem, so that's the definition of a equilibrium constant, right? So how we develop that equilibrium constant. So by definition, the equilibrium constant, right, is Kc, is equal to the rate of this rate constant, right? This K is different, right? So it's a rate constant of the forward reaction divided by the rate constant of the reverse reaction. So spotlight, right? Right, so this K here is a lowercase k, right? So those are the rate constant, right? So. Right, everybody okay with the connection?
160.
Yes.
So number two, so number one, like if you do the calculation, we know the forward rate constant, we know the overall equilibrium constant, right? So we can calculate the rate constant for the reverse reaction. Excuse me, guys. Be quiet, please. Be quiet, please. Right. So second one is the test on the definition of a chemical equilibrium. Right. So for when the systems are equilibrium, we said the rate of the forward reaction is equal to the rate of the reverse reaction. And when that happens, the concentration of the reactant and the products, right, will remain constant. So if you look at this plot, right, so before the equilibrium is reached, right, the concentration of the reactant and the products changes. But as the equilibrium is reached, you can see the concentration no longer changes, it remain constant. Right, so that's the definition of the chemical equilibrium. So I'm gonna unmute you guys. So if you guys have questions, you can speak up right away. Unmute. Okay. So number three, which of following has an effect on the magnitude of an equilibrium constant? I mentioned that only a change of temperature will change the magnitude of an equilibrium constant or the K value. Right. So all the other choices, if they change the equilibrium position, right? If they change the equilibrium position, right? More reactant produced or more products produced, right? So that those factors, those changes will change the equilibrium position, but will not change the magnitude of the equilibrium constant. Right. So we have to be careful with that. So number four, we want to calculate the, we want to predict, right? Predict the shift of the reaction, right? So in this case, we know the equilibrium constant Kc value, and we know the starting concentration of all the substance involved in this reaction. So we want to determine which direction, right, this net reaction persists. Right? So remember, in this type of problem, we have to compare QC, right, with Kc. Right? So QC is the reaction quotient, right? So that could be any time during this reaction, right? So based on the concentration of all the substance involved in this reaction. Right? So even QC is greater than KC, that means the reaction will proceed to the left. Right? So it will generate more, so meaning more products will be reacted into reactants. And so when QC is less than KC, and that means the net reaction will proceed to the right. So more reactant will react into products. Right. So in this case, because all the concentration are given, so we can plug those concentrations into this QC equation. Right. So after you've done the calculation, QC is equal to 700, right, which is greater than the KC value. Right. So when QC is greater than KC, the reaction will proceed to the left. And so the right answer should be B. Oh, how do I get rid of this? Clear my drawings. Right, cool. So number 5, that's a test on the expression for QC. Right, so we highlighted that when your reaction involves a solid or pure liquid, right? So when it involves solids or pure liquid phase, right, those substances do not appear in this QC expression. Right, so in this case, we have two solids, zinc and silver. Right, so they will not show up in the QC expression. So we're only looking at this aqueous phase. If there's a gas phase involved, we also include those. Right, so in this case, we only have this aqueous phase. Right, so only the zinc cation and the silver cation will appear in this QC expression. So on the product side, we have zinc. The coefficient is 1, so there's no exponent. But silver, because there is a coefficient of 2, right? So that 2 becomes the exponent. So it's a silver square, right? So this will be the expression for this QC, right? So that will be choice E. So that will be E. So number 6. Right, so number 6 is a test on how to convert the equilibrium constant. Right, so when we modify a chemical reaction. Right, so the general rule is that, right, if we flip the reaction, right, if we change size, so the K value will be 1 over K. Right, so when we change size, we said we multiply a negative 1. Right, so when we multiply negative 1, so for the reaction, right, if it's flip side, that means we multiply a negative 1. So the K value will become 1 over K. Right, so for a reaction, if we do not switch side, but only say multiply all the coefficients by a factor of n, right, so the K value will become K to the exponent of n. So that's how we adjust this equilibrium constant. Right, so in this question, we have first reaction and second reaction. You can see to get the second reaction from the first reaction, we need to first reverse the reactants and products. And then we have to multiply all the coefficients by a factor of 2. Right, so if the reaction 1 has an equilibrium constant of K1, and reaction 2 has a K2, right, so to get from K1 to K2, so first we have to flip it. Right, so K1 will become 1 over K1. And then we have to adjust the coefficients, right? So we have to multiply all the coefficients by 2. So that become 1 square over K1 square. Right, so for 1 square still equal to 1. So K2 is actually equal to 1 over K1 square. Right, so we pick this choice B. Right, so if we multiply all the coefficients by 3, so this exponent will be 3. Right, so let's continue. So next problem, right? So that is a task on how to determine the shift of a chemical equilibrium, right? So the shift of the equilibrium position. So this reaction involve all the substance as a gas phase, right? So for this one, we say the partial pressure of hydrogen is doubled, right? So let's see, the hydrogen is one of our reactants. Right? So when its partial pressure is doubled, remember partial pressure of hydrogen, right? Partial pressure of hydrogen is mole fraction, right, divided by the total pressure of the system. Right? So the mole fraction of hydrogen gas is actually the number of moles of hydrogen divided by the total number of moles of all the gases. Right? So total number of moles. So here basically when the partial pressure of hydrogen doubled, that means right the number of moles of hydrogen is doubled. So basically the concentration of the hydrogen gas right doubled or increased. Right, so when we increase the concentration of the reactant or one of the reactant, the equilibrium will shift to the right. Right, so meaning that a net reaction will happen right until the equilibrium is re-established, and that net reaction will proceed to the right. So more products right, will be generated. So in this case, the amount of hydrogen gas increased, right? Those increased amount will consume some of the CS2, right? So the CS2 concentration will decrease, right? So, and they will generate more CH4 and the H2S, right? So among all the choices, right? So this after this hydrogen is doubled, right? So it will react with the CS2, right? So at the beginning it increased, right? So that's the moment we double the partial pressure, right? Then it will react, right? So CS2 and the hydrogen during the net reaction, their concentration will decrease, and for CH4 and the H2S, their concentration will increase, right? So C will be the correct answer. Clear my drawings. So number 8, there's delta H involved, right? So we know that this reaction will be affected by the temperature, right? So to conclude, right? So if we have a delta H that less than 0, that means the reaction is isothermic. Right? So it's a isothermic reaction. So isothermic reaction meaning the heat is released, right? So we will put the heat on the right hand side, on the side of the product. Right? So we can treat the heat as a substance. Right? So when the temperature increases, that means the concentration of the heat also increased. Right? So all the other way. Right? So if the question asks, right, so which of following will decrease the concentration of CO2? So CO2 is the reactant, right? So we want the concentration of CO2 to decrease, meaning that we want to consume it, right? So we want to change some reaction condition to further consume this CO2, meaning that we want the reaction to proceed to the right, right? So if the net reaction, right, proceed to the right, that means the CO2 will be consumed, right? So among all choices, right, B, lowering the temperature will cause a shift to the right because you lower the temperature, meaning lowering the heat, right, lowering the concentration of the heat. So this decrease, that will cause the equilibrium shift to the right. right? So more CO2 will be consumed. Right, so if the reaction has a delta H greater than 0, that means it's an endothermic reaction, right? So in this case, if the delta H is greater than 0, right? So I'll erase this. That's an endothermic reaction. So you want to put heat on the left-hand side, right? Because heat is required for the reaction to proceed, right? So if you want more CO2 to be consumed, you're gonna increase the temperature, so increase the amount of heat. So that will cause the reaction shift to the right. So more CO2 will be consumed. All right, let's continue to number 9. So number 9, we're comparing the strength of the acid. Right, so we have a few scenarios. Right, so if we're only looking at this non-metal hydrides, right? So for example, hydrochloric acid, hydrofluoric acid, hydrobromic acid, hydroaldic acid, right? So here, because this all of them are covalent molecules, right? So there's a single bond between hydrogen and the non-metal. Okay. They said the rule is we're gonna look at the electronegativity of these non-metals. So we're basically comparing how strong each bond is, right? So the weaker the bond, the easier for the non-metal to donate the proton or the hydrogen, right? So it's easier for the hydrogen to leave the non-metal, right? So to generate that proton. So that means the acid will be a stronger acid, right? Because the strength of acid is the ability of the acid molecule to donate that proton, right? So that means the weaker this bond, the stronger the acid. I mean the opposite. I'm sorry. The stronger this bond, the weaker the acid, right? So the weaker the bond, the stronger the acid. Yeah. So when we look at this electron negativity, right? So fluorine is the one has the highest electron negativity. So that means this hydrogen fluorine bond is the strongest. So it's very difficult for this hydrogen to leave this fluorine. So it will be the weakest acid, right? For this HI, because iodine has the lowest electron negativity, right? So it's very easy for that proton to leave because this bond is weak. Right, so this will be the strongest acid among all. Right, so when you have this multiple oxygens, right, plus this non-metal, right? So for this type of acid, we're gonna first look at the number of oxygen atoms when the non-metal is the same, and also be careful how does this hydrogen bond to this polyatomic group. And so this hydrogen, although in the formula is written next to the non-metal, but actually it's bonded to oxygen, right? For example, for HClO3 for this one, right? So the hydrogen is actually bonded to one of the oxygen, and the oxygen is bonded to the chlorine, right? So in this case, that's the chlorine, right? Then the other oxygens are also bonded to chlorine. Right, so you're looking at the bond strength of this HO bond here. Right, so the bond strength, right, of this HO bond is determined, right, by what is attached to this oxygen. Right, so the more oxygens we have, right, on this non-metal, so oxygens are very electronegative. Right, so that means there are more electrons will be pulled away from this HO bond region. Right, so because all these groups are electron negative, they're gonna pull the electrons. So the electrons, right, is gonna be pulled to this side. So there will be less electrons available between the oxygen and the hydrogen. So that will make this bond very weak. And so that will make the acid stronger, right? So this proton will be, this hydrogen will be easier to be deprotonated. Right? So that's how we compare the acidity or the strength of the acid. Right? So for the same nonmetal, the more oxygen, so the stronger the acid. And if you compare this these two, right? If you compare these two, so they have the same number of oxygen. So you have to compare the electronegativity of chlorine and bromine, right? So in this case, chlorine is more electronegative, right, than bromine, right? So that means there will be more electrons put to this side again, right? So make that bond weaker, right? So HClO2 will be stronger than HBrO2 in this case. Right, so if you have the same number of oxygen atoms, you compare the electronegativity of this nonmetal, right? The higher the electronegativity, the stronger the acid. Right, for the same nonmetal, the more oxygen atoms, the stronger the acid. So number 10, as which of the following acid will have of solution will have a highest pH, right? So here it's basically a test of calculating the pH when the pKa is given, right? So in the lecture we mentioned that, so the pKa is actually related to the acidity or the strength of the acid, right? For the same type of acid, right? So the higher the pKa, the weaker the acid, right? pKa is the native log of a Ka value, right? So if a pKa is closer to 0 or very small, that means the acid is very strong, right? So if the pKa value is bigger than 7, right? So close to 7 or even bigger than 7, that means this acid is very weak, right? So in this case, we have a 0.1 molar of each of these nonmetal hydride acids, right? So if just by looking at these 4, right, A, B, C, D, I know that for the same concentration, right, this HA will be the weakest, right, because it has the highest pKa value, right? So if I want to calculate the pH of this 0.1 molar HA solution, I can list the ICE table, right? So this weak acid will only slightly dissociate because of this very high pKa value, right? So means that K value for A will be 10 to the negative 11.89. So that's a very small number, right? So we can assume that X is very small, right? So to calculate Ka, right? Ka is given, right? So that will be equal to the equilibrium concentration of X, which is the proton and the conjugated base, right? So X squared divided by 0.1. We assume 0.1 minus X is close to 0.1, right? So we know the value of Ka, so we can calculate the proton X. X is the proton concentration. Right, so this is the proton concentration. And we can convert that into a pH. So to convert the proton concentration into pH is the native log of a proton concentration. Right. 10 to the negative 6. So that the weakest acid gave us a pH of 5.4. Right. So for the B, C, D, right, because this pKa value is lower, that means the Ka value is higher, right? So you don't even need to calculate it because you know these 3 acids are stronger than the first one. So their pH will be lower, right? Because they have the same concentration, right? And the lower pKa value. So you don't even have to calculate. So you're pretty sure that their pH can be lower than the first one. But if you do the calculation, you're gonna find out, right? So they're actually lower, right? So, but for pure water, right? So for a pure water, the proton concentration, right? Remember, for pure water, proton concentration is equal to hydroxide concentration, which is equal to 10 to the negative 7. Right, so a 10 to the negative 7 concentration corresponds to pH equal to 7. Right, so among all these choices, pure water has the highest pH, right? Because this weakest acid gave you a pH of 5.4, right? So water will have the highest pH.
Okay.
So number 11 was the pH of a 0.5 molar base solution, right? So this, you see lithium in the first column, right? First column, second column, hydroxides, they're all strong bases, right? So lithium hydroxide is a strong base, meaning that when you put it in water or when it's a solution, it completely dissolves, right? This ionic compound completely dissociate. So it gives you the metal cation and the hydroxide. So 0.5 molar of this base also corresponds to 0.05 molar of hydroxide concentration. Right, so if you know the hydroxide concentration, you can calculate POH. Right, so remember, if you know the proton concentration, right, so you can get the pH, right? pH is the native log of proton concentration. So similarly for POH, if you know the hydroxide concentration, right? So the POH is gonna be the native log of a hydroxide concentration.
Mm-hmm.
And we know pH plus POH is equal to 14, right? Because KW is at room temperature equal to 10 to the negative 14, right? So the pKW is equal to 14, right? Equal to 14, which is equal to pH plus POH. Sorry, it's POH. Right, so if you want to know the pH, you can first calculate POH. Right, so POH for this solution is 1.3. Right, so pH will be 14 minus POH. Right, so that will be 12.7. Right, so remember there's a relationships between pH and the POH, and also the relationship between this pH and the proton concentration. Right, so if you know another approach to solve this problem is if you know the hydroxide concentration, right? So you can also first find the proton concentration. Right, so the proton concentration is Kw divided by hydroxide concentration. Right, so Kw is equal to 10 to the negative 14. And the OH is 0.05. Right, so now you can calculate the proton concentration. Right, then convert that proton concentration into pH. Right, so the next problem is the reverse of the number 11, right? So it's the reverse process. So the pH is given, so we want to calculate the hydroxide concentration. Right, so again, there are two approaches, right? So in the solution, what I did is first calculate the proton concentration using the pH. Right, so the proton concentration is 10 to the negative pH. Right, so it's equal to 10 to the negative 4.29. And then you can calculate the hydroxide concentration by using Kw divided by the proton concentration. Right, so that will be the hydroxide concentration. Another way you can solve this problem is first you can calculate POH. Right, so POH is gonna be equal to 14 minus pH. Right, so 14 minus 4.29. Right, so you can got the POH, right? So that's gonna be 9.71. Right, so for hydroxide, it's gonna be 10 to the negative 10 to the negative POH. Right, so that will be equal to 10 to the negative 9.71. Right, so you're gonna get the same answer.
Okay.
Next one, which pair is it's not a conjugated acid-base pair. Right, so for a conjugated acid-base pair, right, so you're looking for this one proton difference and one charge difference. Right, so the conjugated acid is the one that donates that proton, and after it loses that proton, what's left is the conjugated base. Right, so in this case, A, we have a hydronium and hydroxide. That's a 2 proton difference. Right, so also 2 charge difference. That's not a conjugate acid-base pair. Right, so the other choices you can see they all have 1 proton difference and 1 charge difference. So number 14, we have an acid-base reaction. So an acid and a base generate another pair of acid and base, right? So this is related to that chart in the slides, right? So the rule is that when you have an acid-base reaction, equilibrium equation, the reaction is preferred, right, from strong acid and the strong base generating weak acid and weak base, right? So you want the stronger acid and base generating weak acid and weak base, right? So if you're not sure the relative strength of the acid and base, you can refer to that chart in chapter 18. Right, so in this case, we have the Ka values. Right, so for Ka, for this HSO4 minus, right, so that we have a Ka value here, and for this ammonium, right, so you can see this Ka value for ammonium, right, is much smaller than the Ka value of HSO4, right? So in this case, which statement is correct, right? So the answer is B. The product will be favored because hydrogen sulfate ion, which is this one, HSO4 minus, is a stronger acid than the ammonium ion, right? So based on the K value, we know this, right? So that means this HSO4 minus is the strong acid, right? So if it is the strong acid, after losing the proton, this corresponding SO4 2 minus is the base, right? It's the conjugated base of the acid, right? So that will be the weak base. And the ammonia is the stronger, in this case, right? Compared to this one, is the stronger base than this. So that's the base, right? So in this one, compared to the sulfate, is a stronger base, right? So this is the conjugated acid of ammonia, right? So it is a weak acid, right? So if you try to identify the pairs, right? So this hydrogen sulfate and the sulfate is one pair, and the other pair will be let me change the color here. Yeah, so this will be the other pair. Right, so HSO4 minus is the acid, and this is conjugated base. Right, so this is the base, ammonia is the base, and the ammonium is the conjugated acid. Right, so we know this reaction will proceed to the right, right, because this side is stronger than the right hand side. Left hand sides are stronger than the right hand side. Right, so number 15 asks which mixture give a buffer system. Right, so for a mixture to be a buffer, right, so you must have this common ion effect, right? So you want this two species generate the same type of ion or same ion, either cation or anion, and this cation or anion must be a must be a part of the weak acid or weak base, right? So in this case, choice B, right? So we have a carbonic acid and this bicarbonate group, right? So when they dissociate, so when carbonic acid dissociate in water, right, it gave you proton and the bicarbonate, right? So bicarbonate will be the common ion, and this is a weak acid, right? So that will generate a buffer. So the other choices, they don't have a common ion, right? So they cannot be a buffer.
Okay.
So number 16, which one of the volume had the highest buffer capacity? Right, so for a buffer capacity, we look at two things, right? First is the absolute concentration, right? So that is the magnitude of the concentration, right? So a good example will be if you compare A and D, right? So they have the same ratio of the acid and the base, right? So they have the same component, same concentration ratio, right? But for D, its absolute concentration is higher, right? So the higher the absolute concentration, the higher the buffer capacity. And when the absolute capacity is similar, we also look at this ratio, right? So relative concentration of this acid and base ratio, right? So the closer this ratio is equal to 1, the higher the capacity, right? So in this case, D will be the best choice, right? So D will be the best choice because it has the highest absolute concentration, and also the relative concentration is equal to 1. So that will give the highest buffer capacity. Right, so meaning that if you add the same amount of strong acid and base into this 4 buffer system, the change of pH in this solution B will be minimum, right? Because the buffer has the highest capacity. Number 17, right? So when a strong acid is titrated with a strong base, what's the pH of the equilibrium point? That will be equal to 7, right? So every time you have a titration between strong acid and strong base, right? So you have a equivalence point equal to pH of 7, right? So strong acid completely dissociate, give you proton. Strong base completely dissociate, give you hydroxide, right? So that will give you water, right? So that corresponds to a pH of 7. Right, so when you have a weak acid and a strong base, right? So if you have a weak acid and a strong base, so for the weak acid, you're gonna start, right? So start with a relative higher pH, right? Because the acid is weak, and you have this buffered region at the beginning, and then this after the equivalence point is looks the same as the strong acid strong base curve, right? So in that case, right, the equivalence point, say if this is a pH equal to 7, the equivalence point is gonna be greater than 7, right? Because at the equivalence point, all the weak acid has been converted to its conjugated base, right? So that conjugated base, right, is a weak base, so that will be basic, right? So means pH is gonna be greater than 7, right? So if you add a strong acid into weak base, right, so you have this buffered region at the beginning, and then it's gonna be similar to this region right, but the opposite direction, right? So the equivalence point, right? The pH is gonna be lower than 7. Right? So if, for example, this is pH 7, so the equivalence point is gonna be have a pH lower than 7 because at the equivalence point, all the weak base has been converted to this is a conjugated acid, right? So it's an acid, so it will generate some little bit proton, so making the solution a little bit acidic. So the pH is gonna be less than 7. Right, so number 18, right? So we already explained that, right, in the previous problem. So we add, so alpha switch curve represent the titration of a weak acid with a strong base, right? So the answer will be B, right? So this one. So you can see the starting pH is relatively higher, right? So this will be the strong acid and strong base, right? So this will be the strong acid and strong base, right? So this relative starting pH, right? So you can compare this is higher, so that must be a weak acid, and then you titrate it with the strong base, right? So in this figure, the equivalence point is about here, right? So it is greater than 7, right? So this will be the titration curve between the weak acid and the strong base. So number 19 is the it's related to the solubility, right? So calcium hydroxide, we have a saturated solution. A saturated solution, you can obtain a saturated solution by adding this barely soluble compound into water, right? Then filter out that solid, so that solution is the saturated solution, right? So in this case, you start with a saturated solution and you add more solids into it, right? And then you add strong acid. So what happens to this equilibrium, right? So because this solid, right, is calcium hydroxide, it contains hydroxide, right? So when it dissociates, it generates this hydroxide. So adding the acid, right? The acid meaning adding proton, that proton will neutralize this hydroxide, right? Causing this hydroxide concentration to decrease. Right, so when this hydroxide concentration decreases, more solid will be dissolved, right? So because the reaction will be shifted to the right, so more solid is going to be dissolved, so increasing the concentration of the calcium cation. Right, so also because at the same temperature, this Ksp is constant, right? So this Ksp in this case is equal to calcium concentration times the hydroxide concentration squared. Right, so meaning that if one of the concentration goes down, the other one must go up. Right, so if you add acid that decrease the hydroxide concentration, so the calcium concentration must go up. Right, so the correct answer should be B. So number 20, this one is easy. So this expression for the dissolution of calcium phosphate. Right, so calcium phosphate, right, so it's an ionic compound, right? So for the part it can dissolve, it will generate the corresponding number of metal cation and the polyatomic anions, right? It has 3 calcium, 2 phosphate, right? So that will give you 3 calcium, 2 plus, and 2 phosphate. So this should be 3 minus, sorry. Right, so the Ksp will be the calcium concentration to the third, phosphate concentration to the second. yeah, you have this coefficient. Right, so the answer should be this C. So let's go to the short answer. All right, so the first one is related to chapter 17. Right, so you have this chemical reaction. Right, so 2A generates 1B and 1C. Right, so you may know the Kc value. And we know the starting concentration or the initial concentration of everything involved in this reaction. So the number of moles and the volumes are given. Right? So we want to know what happens, right? So what happens to this chemical reaction or based on the initial concentration. Oh, we have the starting concentration of B and the C. Okay, we don't have any A, but we have a B and a C. Right, so we know some of A gonna be generated. Right, so first I will convert this number of moles into concentration. Right, so for B and the C, I use number of moles divided by the volume. So that will give me the molar concentration. So that will be the starting concentration for B and the C. And then we have zero concentration of A at the beginning. Right, so in this case, I'm pretty sure that A is gonna be generated. So because of a coefficient of 2, so the change will be plus 2x. So for B and C, it's going to be minus x. So this will be the final concentration at equilibrium. So for Kc, I'm going to plug in those equilibrium concentrations. So be careful, you have a square here. So it's very easy to forget about this square. After you look at this equilibrium concentration, you plug those in. But remember, this A has a coefficient of 2, right? So you must have a square here, right? So you can solve for this equation to calculate x. So x is gonna be, you have 2 solutions, right? So you have to determine which one makes sense in this problem, right? For the second answer, 0.8 is too big, right? If you have 0.4 minus 0.8, you're gonna end up with a negative final concentration, which doesn't make sense. Right, so only one of the solution makes sense. So only 0.339 is the acceptable answer. So that will be the amount of B and C being consumed. Right, so for A at equilibrium, concentration is 2x. So the equilibrium concentration for A will be 2 times the x. So that will be the answer. So for part B, right, so when the equilibrium is reached in part A, you add another 8 moles of B. And they ask what's the concentration of A when the equilibrium is reestablished. Right, so the first step will be figure out the initial equilibrium concentration, right? So what's the concentration of A and B and C when the initial equilibrium is reached, right? So in part A, we calculate that the concentration for A at equilibrium is this, right? So for B and C, this will be their concentration, right? So we add another 8 moles of B, right, into this system, equilibrium system. Right, so 8 moles of B corresponds to another 0.4 molar. Right, so by adding this 8 more moles of B, that will disturb this equilibrium system. Right, so the B concentration will increase to 0.461. Right, so this equilibrium is disturbed, but we know it's gonna reach equilibrium again, right? So we can generate another ICE table, right? So for this net reaction, right? So we can do the same thing, right? So plus 2x minus x minus x. Right, so using this new concentration at the new equilibrium to calculate the x. So in the actual exam, I won't let you actually calculate this. Right, so it's gonna take a lot of time. So all I ask you to do is list the final equation, right, involving x being the only unknown, and you don't have to solve it.
Okay.
Yeah, so that will save you a lot of time. Right, for example, if I proceed with the calculation, right, so it's gonna be something like this, right? So it probably take you 5 to 10 minutes to solve this without a calculator, right? So if in the exam, if you leave your answer like this, without solving the x, I will give you full credit. Right, so in this case, I solve for x, right? So that's the amount of A generated in this net reaction, right? So for the new equilibrium concentration of A is the addition from the starting concentration, right? And adding this more A generated during this net reaction. All right, so for second one, we have a weak acid and has this proton concentration, and they ask for the Ka value. Right, so this is pretty straightforward. We can convert this proton concentration right, into in this ICE table. Right, so let me put down a little bit. Right, because it's a weak acid, right? So when it dissociate, it will give you the same amount of proton and its conjugated base. Right, so we start with 0.05 molar. Right, so all the coefficients are equal to 1. So we can use minus x for the acid plus x for the products. Right, so in this case, we know the proton concentration generated, right, is given. So that will be equal to x. Right, so the same concentration for the conjugated base. And for the acid, right, so that will be 0.05 minus this x. Right, so the Ka, we can calculate it, right, using the products divided by the reactant. So in this case, I use 0.05 instead of 0.05 minus x. Right, so in this case, because I assume this K is a weak acid, right? So I assume this x is small. Right, so I don't have to, so I can say 0.05 minus x is approximately equal to 0.05. Right, so I can use this only instead of 0.05 minus x. So after you've done this and got the result, right? So you have to do the justification. Right, so in this case, we can see x is this value, right? So you can compare this value with 0.05. Right, so if it's less than 5%, that means our assumption is good. Right, if it's greater than 5%, we can no longer use this directly. We have to use 0.05 minus x. That will complicate the calculation. Right, so but generally when you have a weak acid and a weak base, or a ionic compound with a low solubility, right, by looking at this KST value or KB value, this assumption is almost always valid. Right, so but if you have a fairly large K value, like 10 to the negative 2 or 3, you have to be careful with this assumption. So next one is a acid-base titration. Oh no, it's a buffer system. Sorry. So you have buffer system. So this phosphate buffer. So it asks us what's the pH of this system. Right, so we have sodium, right, dihydrogen phosphate and sodium hydrogen phosphate. So they all sodium salts. So they completely dissolve, right? So they will generate this common ion, which is not the common ion. This H2PO4 and the HPO4 2-. But this H2PO4 will also dissociate and give you proton and HPO4 2-. Right, so now you have this common ion effect. Right, so that's why it's a buffer system. Right, so in this system, right, so in this system, you have the H2PO4 dissociate and give you HPO4. And based on the problem, we know the initial concentration. So that's the initial concentration in the IC table. And this is a change of concentration. Let me zoom out a little bit. Let's see. Right, so this is better, right? So we can use the IC table and the given Ka value. Right, so Ka value is given, so we can plug in these terms into this equation. And again, here I assume that x is small compared to 0.2 or 0.4. Right, so here I use 0.2 directly instead of 0.2 minus x. Right, so I solve for x. And then you have to write down that justified it, right? So this 3.1 times 10 to the negative 8 divided by 0.2, right? So this is way smaller than 5%. Right, so that means this assumption is valid. So by converting this x, which is the proton concentration, into pH, we got a pH of 7.51. About 2 minutes left. Let's hurry up. Right, so next one is a acid-base titration. So we have a weak acid. Why is weak? Just look at this Ka value, right? So it's 10 to the negative 5. So we know it's a weak acid. So we titrate it with sodium hydroxide, which is a strong base. Right, so it asks us what's the pH of the solution after 22 milliliter of sodium hydroxide have been added. Right, so when I do this type of problem, we can use this equation. Right, so pH is equal to pKa plus negative log of base divided by the acid. Right, so you have to, you know the Ka value, so you know pKa. Right, so all we need to do is figure out the concentration of the conjugated base of the weak acid and the amount of acid left after this base has been added. Right, so for this weak acid, when they react with a strong base, which is hydroxide from sodium hydroxide, right? So this reaction will proceed to completion, right? So generating water under the conjugated base of the weak acid. So this conjugated base of the acid, the amount is equal to the hydroxide from the strong base. Right, so we add 22 milliliter of sodium hydroxide. So the number of moles of hydroxide added will be concentration times volume, right? So that's 0.0066 moles, right? So that means 0.0066 moles of this conjugated base has been produced. Right, so at the beginning, for the acid HA, at the beginning we have 0.0075 moles, and 0.0066 has been consumed. So the difference is how much left. Right, so we have 0.0009 moles of acid left, and the 0.066 conjugated base generated. Right, so we want the concentration ratio of this conjugated base and the acid. Now we have the number of moles, but they're in the same system, right? So the volume is the same. So after you add 22 milliliter, they have the same volume, right? The volume is consistent. So you divide the number of moles by the same volume. That doesn't change the ratio of this, right? So you can use the ratio of the moles directly, right? Because if you convert them into concentration, you divide the volume on both numerator and denominator, so you're gonna end up with the same ratio. So I can use this number of moles directly here, right? So that will give me a pH of 5.75.
Okay.
Right, so remember using this equation. Right, so for part B, how much of this sodium hydroxide is required when the pH of the system equal to the pKa of this weak acid. Right, so for this one, remember that when we look at this acid-base titration curve between the weak acid and the strong base, right, so the halfway to the equilibrium position, right, so equivalence point is here, right? So the halfway to the equivalence point, the pH is actually equal to pKa, right? Because when it's halfway to the equivalence point, you have a 1-to-1 ratio between this conjugated base and the acid. Right, so at this point, the pH is equal to pKa. So all you need to do is find out the volume of required at the equivalence point, right? So the half of the volume will be the volume at this point. Right? Mm-hmm. So to achieve equivalent point, you want the amount of hydroxide added, right, equal to the amount of the weak acid, right? So you start with this much of weak acid, right? So using the M1V1 equal to M2V2, right? So this is the acid, and this is the concentration of the base. So this is the amount of base required to achieve that equivalence point. Right, so that it corresponds to 25 milliliters. So half of that is 12.5. Right, so remember this point, right, halfway to the equivalence point. Right, so you're gonna see a similar problem in the actual exam on this. Mm-hmm. So the last problem is a solubility problem. Oh, I don't have it in my scanned file. Hold on. Let me pull that out. Midterm practice. So for the last problem, I actually didn't finish that because the assumption we made, right, is not a valid assumption, and I will show you why. Right, so for this compound, right, we have magnesium, right, dissociate into magnesium 2+ and the sulfate. Right, so in this case, we place that into a 0.1 molar of this magnesium chloride solution. So this is not a solid, right? It will totally dissolve. right? So the initial concentration is already 0.1. So this is plus S. So the equilibrium concentration is 0.1 plus S. And this is S. Right, so this is S. So based on the KSP value, so KSP is actually equal to 0.1 plus S, right, multiply S. Right, so in the solution I posted, I assume this S is small. So I did was a 0.1 times S and solve for the S. But in that case, your S is going to be equal to 5.9 times 10 to the negative 2. Right? But if you compare that into a 0.1, that is greater than 5%. Right? So you cannot make this assumption that S is relatively smaller, way smaller than 0.1. So you cannot do this. Right? So in this case, you must use this equation directly. Right? So you must solve for this X. So if you do that, you're gonna get S equal to 4.2 times 10 to the negative 2. Right, so that will be the solubility for this magnesium sulfate. Right, so I will post the last page, right, the solution for the last problem on Moodle right after this. All right, so the last problem is a good example of why we need to justify our assumption. Right, so in this case, if you use 0.1 directly instead of 0.1 plus S, the answer has an error greater than 5%. Right, so that's the case that your assumption is not valid. Right, so you must proceed with this calculation. All right, so that's it.
Professor Zhang, what chapter was number 6 from?
Number 6?
Yes.
I You mean the number 6 multiple choice?
Yes.
All right. Oh, that's number chapter 17.
Okay.
Yeah, I think we talk about this in the lecture after the spring break.
Okay.
Yeah.
Thank you.
All right, the exam will have a very similar number of problems, but more calculation related problems, right? So you have the whole day. Right? So again, it's open note, open book, open internet, and make sure you upload it before the midnight. And this solution I uploaded, that's the one I use the Genie Scan app. Right, so I scan every page and convert all the pages into a PDF.
Is it timed or do we have like all day to complete it?
You have all day. I'm gonna post the exam like in the early morning. So when you wake up, you should be able to see it. You can download it, either print it or like answer it electronically and then upload it before midnight.
Okay.
All right, I have to end this meeting because I have another one after. So if you guys have any question, the fastest way is text me or FaceTime. You know, I don't check email that often compared to the rate I check my message. So any questions, you know, today, tomorrow, just message me. All right.